The diagram in front of you shows a simple circuit where a motor is connected to a battery. Initially the switch is open, so there's no current flowing through the motor, and obviously once we close the switch, a potential will be across the motor and it'll start to spin. When we solve these kinds of questions, we need to simplify it. A motor is basically just a whole bunch of windings of small copper wire. So basically a motor is just a resistor. So initially, before the motor spins, it's not generating any back EMF. Remember, a motor and a generator are one and the same. As soon as a motor starts to spin, it generates its own EMF in the opposite direction. Initially, when I close the switch, because the motor is not spinning, we can think of it as just a resistor. So let's draw this in. Okay, you see that the motor is drawn as a simple resistor of value R. So now when the switch is closed, initially we have a circuit that we can solve using Ohm's law. So what does that look like? Using Ohm's law, all we need to do is use V is equal to I times R, where V is our voltage of our battery initially, I is the current running through the windings of the motor, through the coils, and R is the resistance of the motor itself. So if I want to solve for the current running through the windings initially before it starts to spin, it's just V divided by R. Nothing unusual about that. Now when the motor starts to spin, it generates its own EMF in the opposite direction, a back EMF. So let's draw what that circuit looks like now. We see now that the switch is closed. We're assuming the motor is spinning up to its full potential, and it's now generating its own voltage in the opposite direction, which we're going to call V back. Notice that the positive side of this battery that we've drawn in here to represent this back EMF is directly connected to the positive side of our original battery. Just examining the batteries, we'll see that those two voltages will actually cancel each other out, and I can simplify the circuit once more. So for example, if I just make up some numbers here, let's imagine my original battery's voltage was 100 volts. And let's say once it's spinning up to its full potential, it generates a back EMF of 85 volts. The net voltage that's actually driving the current in that circuit will just be 100 volts minus 85 volts to give me 15 volts. So again, I can use Ohm's law and figure out what the current is running through that circuit with this new voltage. The only thing that I've changed is the value of V. Instead of being 100 volts when it isn't spinning, it's now 15 volts. The resistance of the motor does not change. So now let's look at how that actually helps us. Let's finish the question by making up some more numbers. Let's imagine the resistance of the windings of the motor, and they're generally small because it's just wire, is 10 ohms. So initially, my current is 100 volts because it's not spinning. It's just starting up, divided by 10 ohms. And when I do that, I end up getting 10 amps. In the end, once the motor is up to full speed, my net voltage has diminished to 15 volts. My resistance is still 10 ohms, and I end up getting 1.5 amps. So when it's running at full potential, my current is only 1.5 amps, and when it's not spinning, in other words, if I hold the motor or if I just start it up, the current soars to 10 amps. So you can see that there's an advantage to a back EMF. It lowers the overall current flowing through the windings, and current generates heat. So when the motor is left to run freely, there's less current running through the windings and the motor stays cooler. When I seize up the motor, or when it's first starting up, the current draw is quite significantly larger, so up to 10 amps in this case. And if it was left this way, in other words, if we kept the motor seized up or kept it under a huge load, eventually those windings would melt and the motor would smoke, and that would be the end of it.